So today we're going to continue our journey into the Gaussian integers. And so we have already established Bezo's lemma. We've talked about what it means to be relatively prime. We have proven the linear combination lemma. We have proven now almost every result necessary to prove a fundamental theorem of arithmetic for the Gaussian integers. And that's the plan for today. We're going to go ahead and finish the loose ends that we need to establish the fundamental theorem of arithmetic. And our first result in that direction is by proving Euclid's lemma. And if you recall, in our lessons on proving the fundamental theorem of arithmetic, Euclid's lemma was the last hurdle we needed before proving the fundamental theorem of arithmetic. And that's going to be the idea here. And so the way we are going to go about today's lesson is by going back to the results we did over the integers and then doing the same thing we did last time, where we go ahead and compare the two results, the one in the Gaussian integers and the integers, and then make the changes necessary so that the proof holds. So here is the Gaussian Euclid's lemma. And what it says is if d, m, and n are Gaussian integers such that d and m are relatively prime, if d divides m times n, then d divides n. And so let's go ahead and prove this, but first let's go back and recall the statement for the integers and how we proved it. So here's the original Euclid's lemma as it is covered in the book. And it's in the setting of the integers. And the proof is relatively short. It relies on Bezo's lemma, which we now have. So let's go ahead and copy this proof over to the one with the Gaussian integers and see what are the things we need to change in this proof so that it holds over the Gaussian integers. So here we have the statement for the integers. So I've gone ahead and copied it over. And now let's go ahead and then translate all the statements, the whole proof into the Gaussian integers. And there's only a few adjustments we need to make in this case. So here's the argument. Since d and m are relatively prime, now over the Gaussian integers, we know that the GCD is not unique. And so we don't have necessarily that the GCD is equal to 1, but we know that it's going to be equal to some unit. And so since d and m are relatively prime, there exists a unit in the Gaussian integers such that the GCD of d and m is equal to u. Next thing, we go ahead, just as before, we apply Bezo's lemma. So by the Gaussian, Bezo's lemma, there exists x and y in the Gaussian integers such that we have dx plus dm is equal to u. And so we are now at this stage of the proof. We go as before, we multiply by n on both sides. So multiplying this equation by n yields that we have dxn plus dmn equals u times n. But now we have a bit of a problem because we can't do exactly what we did before, because now we have by linear combination lemma that d divides n times u. And so what we are going to do so we can get d divides n is to multiply. So we can do it in there's two things we can do. We can multiply by u inverse, the multiplicative inverse of u, and get that over here, or we can go directly. And so I'm going to go ahead and do this directly here. And so by linear combination lemma, we have that d divides u times n. So in particular, there exists a w in the Gaussian integers such that we have that d times w is equal to u times n. And now since u is a unit, its multiplicative inverse, which I'm going to write as u to the negative 1, is in the Gaussian integers. And thus, we have that dw is equal to un is the same as dw u inverse equals n. Because on the right hand side we're going to have u times u inverse, which is 1, and so we have that the right hand side would just be equal to n, and thus d divides n. And so that concludes it. We could have another equivalent approach, which is what I mentioned verbally, is we can go ahead and take this u inverse and multiply both sides of this equation by u inverse. In doing so, we're going to have dxn times u inverse plus dmn times u inverse. But then over here, we're just going to have an n. And so then we're going to have, by linear combination lemma, that since d divides this and this, we have that d divides the right-hand side, which will now be which will just be n, so d divides n. And so that's an equivalent way of going about this. But now we are done with the Gaussian Euclid's lemma. And the key thing is, because we have Bezo's lemma, this codes. And this is the general theme for abstract algebra and commutative algebra for that matter. Once you can establish a Bezo's lemma, then Euclid's lemma, this argument here, will just hold in generality. And so that's one of the aspects of degeneralization, is that we have moved over to a larger ring, the Gaussian integers. But because we have Bezo's lemma, we can go through and prove these statements in the way that we are doing right now. So now the next statement we want to do is the fundamental property of primes in the Gaussian integers. And so this is recall that in the case of the integers, this is what Euclid originally proved. This is his original lemma. And so what it says is, if we have a prime p in the Gaussian integers in this setup, then the Gaussian, if p divides a times b, then p divides a, or p divides b. So let's go ahead and prove this result, but let's go ahead and do the same thing we just did with the previous result. Let us revisit the original proof that we did for z. And so here's our original proof of Euclid's lemma over the integers. And so we go ahead and apply Euclid's lemma, and then we take d to equal p, and we run through the argument in that way by contradiction. So let's go ahead, copy this, and then just run through the same exact argument over the Gaussian integers. And what we will see is that the whole proof holds verbatim in this case. So now we're going to go ahead and see that the proof just holds exactly as what we did in the integers. So let's go ahead and see this. So we're going to go back towards a contradiction. Suppose that p does not divide a and p does not divide b. Then we have that since p divides ab and p that does not divide a, actually let me write it this way. So since p does not divide a, we have that p is relatively prime to a, and by assumption p divides a times b. And now we apply lemma 1 to 2.1, because in this case we have p and a, which is now a is taking the role of m, p and a are relatively prime, and we know that p, which is now taking the role of d, that p divides a times b, so p divides b, which is our desired contradiction. And so, so by lemma 1 to 2.1, p divides b, which is a contradiction, And thus, we can conclude that P divides A or P divides B. And so that finishes the argument. But again, the proof is exactly the same that we had over the integers. We just have to tweak it just slightly. And then for homework, you're going to go ahead and do the extension of this result. Specifically, that if we have a Gaussian integer that is a prime, namely P, and we have that A1, A2, all the way through AR, are Gaussian integers. If P divides the product of A1, A2 all the way through AR, then P divides A sub j for some j equal to 1, 2, all the way to R. And you already have done this question in the homework that we did in this section on Euclid's lemma at the start of the term. And what you'll see is that the proof, just as the ones we have done today, will be essentially the same, just a slight tweaking where we see integers, replace it with Gaussian integers, and make the necessary adjustments, and your proof will just hold. And that's the beauty of the Gaussian integers as we are covering, is that new terminology, new structure, but these properties that we are used to continue to just we are able to continue to extend them and show results like Euclid's lemma. And now we are off to prove the fundamental theorem of arithmetic, because we have everything at hand. And so the fundamental theorem of arithmetic, or the fundamental theorem of Gaussian arithmetic, this is due to Gauss. And so this was proven in the 1830s. And the way that Gauss came about this was by trying to understand the law of quartic reciprocity, which Eisenstein would later prove some 15 years later. And Gauss, and this is the reason why we give the name the Gaussian integers, Gauss studied many of the properties we have been seeing for the Gaussian integers in that decade of the 1830s. So he established the norm, he found the division theorem, he proved the fundamental theorem of Gaussian arithmetic and was able to make these connections. So let's go ahead and prove this. And so just a bit of a caveat, I'm going to go back to the proof, but for homework I'm going to task you with proving the existence. So existence will be an exercise. Namely, it will be 13.4.11, and so that will be part of the homework. And so what we will do is prove uniqueness. And so we're going to go ahead and do uniqueness. And so what I'm going to do is, just as we before, I'm going to go back to the original proof, and we're going to copy the uniqueness portion of the proof and then bring it over. There are some things that we have to now do that we didn't have to do in the case of the integers. And that's the following. The fundamental theorem of Gaussian arithmetic tells us that if we have a Gaussian integer z, where z is not equal to 0 and it is not a unit, then we can write z uniquely as a product of one or more Gaussian primes. And the prime factorization of the Gaussian integer is going to be unique up to order and units. The proof that we did for the integers, it wasn't for the integers, it was for the natural numbers. And as a result, it was unique up to order, but we could have easily extended it over to all the integers if we were to say that it was unique up to order and multiplication by -1. And so the units are taking that role of the 1 and -1, but now we have to worry about I, -I, 1 and -1 as well. So let's go ahead and revisit the old proof. So here's our proof of the fundamental theorem of arithmetic. As a reminder, when we did it in the course at the start of the term, we had already done the existence case. And so you want to revisit the case for existence for the homework. And so this proof over here is doing it for uniqueness as well. And so what we are going to do is copy this whole proof and bring it over to the next slide. And we're going to go through induction, just as we did with the original one. So we had a statement S of n, where S of n was a statement that n has exactly one prime factorization up to order. In our case, since we are doing it over the Gaussian integers, we're going to go ahead and extend this statement so that it's exactly one prime factorization up to order and units. And we're going to go ahead and do strong induction to prove this. So now we have the proof here. So we want to go ahead and modify this so that we can apply strong induction. So now we're assuming an existence. Let me just go ahead and write this down. So by existence, we have that every non-zero and non-unit Gaussian integer can be written is prime or is a product of primes. And to be precise, Gaussian primes. And so we have this here. And so we're going to go through the proof as now with that in mind. So we need to do induction. But the thing is, our original statement S of n was that n has exactly one prime factorization, and we need to induct on the naturals. And so how can we induct in this case? Because we want to induct over Gaussian integers. And we don't have an ordering there so that we can do induction. And so we do the next best thing. We're going to induct on the norm of elements. And so specifically, for n greater than or equal to 2, let S of n be the statement if W is a Gaussian integer with norm W equal to n, then n has a unique Gaussian prime factorization up to unit and order. And so we have this statement right here. And so notice that this is exactly the statement we had for our statement S of k in the case of the integers, where we had that the statement was that for every n greater than or equal to 2 has exactly one prime factorization up to order. And so now we have added the up to unit and order. And so in the case of the integers, our base case was automatic because 2 was prime. So let's go ahead and consider now what the base case is for us. And so for us, the base case, of course, is still n equals to 2. But we need to look at those Gaussian integers whose norm is exactly 2. So for the base case, observe that those elements, that if W is a Gaussian integer with norm of omega, W, used to calling it omega, with norm of W equal to 2, then W is going to be plus or minus 1 plus or minus I. So we're going to have each of these possibilities for what our W can be. And so this is the only way we can get back 2. And so to show this, of course, we can say that we have the norm of a plus bi. It is going to be a squared plus b squared. And so the only way we can get 2 is if both a and b in absolute value are equal to 1. And so we're looking at all possible combinations of the form plus or minus 1 plus or minus I. And so that's going to give us, in this setup, 4 different possibilities for what we may have here. But this here is going to have a unique prime factorization. So I'm going to go ahead and just rearrange things. So let's go ahead and now see the following. So we have 1 plus I. So we're going to consider 1 plus I. Then we're now going to multiply by units. So negative 1 times 1 plus I, which is going to be just minus 1 minus I. We're going to have I times 1 plus I. And that's going to give us a negative 1 plus I. And finally negative I times 1 plus I. And that's going to give us 1 minus I. And so we have this here. And so the key thing to see here is that we know that W can only have, there's only 4 possibilities for what the norm of W equals 2 is, and this namely plus or minus 1 plus or minus I. And so one element will be 1 plus I, but we know that we have already established that 1 plus I is prime. But now we have the 1 plus I times negative 1, so times a unit, is equal to negative 1 minus I, so that gives us another one of the possible W's. And so that tells us that 1 plus I and negative 1 minus I have the same unique prime factorization up to order and units. And so that works. If we do I times 1 plus I, then we have minus 1 plus I, and so that gives us one of the third possible W's here, and we also have the uniqueness up to order and units. And finally, if we do negative I times 1 plus I, we have 1 minus I, and that finalizes it because we exhaust the 4 different possibilities. We already have all the different combinations of plus or minus 1, plus or minus I, occurring by considering the 4 possibilities of multiplying 1 plus I times a unit. And so thus, the statement S of 2 is true. And so we have our statement here. And now what we are going to do is do the inductive step. And we want to argue this by breaking it up into the case when it's prime and when it's not prime, just as we did before. So now we're going to go ahead and do this for some n. So next, let W be a Gaussian integer. Actually, wait, hold on. So we're doing strong induction. So now suppose that the statement that S of k is true for each k less than n. And let's go ahead and let W. So I had some trouble with my shared screen, so let me go ahead and recap just in case it didn't refresh. So we're assuming now that S of k is true for each k less than n. And now what we want to take is a W in the Gaussian integers whose norm is exactly equal to n. But there's a couple of things that we need to take into account. It may be the case that the n we choose has no W whose norm is that n. So for example, 3. Are there Gaussian integers whose norm is 3? If that were the case, that would mean that 3 is equal to a squared plus b squared for some integers a and b. And we know from Fermat-sum of squares that that is not the case. And so as a result, I'm going to go ahead. If that were the case, then the statement is still true. Because the premise, while false, that this here would there is no, if we did not have a Gaussian integer whose norm was equal to n, then the statement will still remain true. And so we're going to break this up into several cases. So note that if there is no W in the Gaussian integers with norm of W equal to n, then S of n is true. And so this is just vacuously, since the premise will be false, and false will imply true. And so this S of n will remain true. Now, let's go ahead and suppose that we had a W. So suppose that there exists a W in the Gaussian integers with norm of W equal to n. If W is a Gaussian prime, then there's nothing to show. And so technically, what I am taking into account here that if W is a Gaussian prime, by taking norms, any factorization of W will have to be of the form U times W for some unit U. And so it's going to be unique up to unit in this case. And so that's what I'm taking into account here. And so now let's go ahead and suppose that W is a Gaussian composite integer. So suppose that W is a Gaussian composite integer. And so notice that where we are now is where we left off in the proof. And so now we have, in the original case for the integers, we had if n is prime, then we are done. And now then we suppose that n was composite. And so now what we are going to do is suppose that we had two different prime factorizations for our W in this case. So suppose then if W, and so here we're using the existence, so we know that the W can be written as a product of primes. So if W was equal to P1, P2, all the way to PR, and also Q1, Q2, all the way to Qm, where each Pj and Qj is a Gaussian prime, then we have, by the same argument that we did in the case for the integers, that if we wrote this as P1 times the rest in parentheses, we must have that P1 has to divide, P1 must divide, well, P1 divides Q1, Q2, all the way to Qm. And as a consequence, we have by the corollary that you'll be doing for homework, that if a Gaussian prime divides a product of Gaussian integers, then we have that prime has to divide one of those, in this case, one of those Q sub j's. So we get that then P1 divides Q1, Q2, and this implies by, let me go ahead and just erase a couple of things here. And so we have that P1 divides Qj for some j. So now we're going to do, we can reorder. So reordering if necessary. We may assume that P1 divides Q1. Then we have that there's a unit U1 in the Gaussian integers such that P1 is equal to UQ1. And so we have P1 equals U times Q1 And now we're going to do the same exact argument we did in the case of the integers. We're going to consider our in our case our w divided by p1, and that's going to be equal to p2 through pr. The only difference is that because now we have units, the right hand side is going to be u times q2 all the way through qm. And instead of using the ordering, we're going to rely on the norm. And so we're going to have an inequality in terms of norms, and then the induction hypothesis will give us our desired conclusion. So let's go ahead and finish this off. And so we have here, so then we have that w over p1 is going to be equal to p2 through pr, which is also equal to u1 times q2 through qm. And since the norm of w over p1 is going to be equal to, less than or equal, it's going to be strictly less than the norm of w, and this we can get from the multiplicativity of the norm. The norm of p1 is not equal to 1, since p1 is a Gaussian prime, and so the norm of w has to be equal to the norm of p1 times the norm of p2 all the way through pm. And so by dividing by m, this has a norm strictly less than the norm of w. And so since this norm here, since we have this condition, we have by the induction hypothesis that our prime factorization is unique up to order and units. And so we have the w over p1, the prime factorization is unique up to order and units. But we know that w over p1 is going to be p2 through pr times u1, and then we have q2 to qm. The uniqueness up to order and units allows us to say that after a reordering, we can say that p2 is equal to a unit times q2, and then similarly pr is going to be equal to a unit times qr. And so specifically, so we have the following. So thus, we have that m must be equal to r, and there exists units, and after a relabeling, we have that pj is equal to uj qj for j being between 2 and m, and uj a unit in the Gaussian integers. So in particular, as a consequence now, so thus we get that w equals p1 through pr is equal to u1 p1 all the way through ur pr, where now we have substituted in our values for the qj's in terms of the p's. Oops, sorry, that should have been u1 q1 and then ur qr. So this shows that S of n is true, and by strong induction, S of n is true for each n greater than or equal to 2, which is what we wanted to prove. And so that establishes the result. And now we have the fundamental theorem of arithmetic for the Gaussian integers. And so now we have gone through and gone full circle, and we can come back to our diagram that we had earlier on, where we just went through the same arguments we did for the integers. We talked about a division theorem, a Euclidean algorithm. We found the necessary and sufficient condition for linear Taylor-Fenton equations, over the Gaussian integers. We did a Gaussian Euclid's lemma, and finally we have the fundamental theorem of arithmetic for the Gaussian integers. And so now we are one step closer. We've climbed another mountain to prove this. And one of the things that we are going to see is that now we're going to start building. So in our next lesson, we are going to prove the Fermat sum of squares theorem once more using the Gaussian integers. And from there, we're going to start to trek upwards towards Fermat's last theorem and see what was known through the 1800s on Fermat's last theorem. So in an earlier lesson, we saw that if we had a Gaussian integer and we knew that the norm of that Gaussian integer was prime in the integers, then the Gaussian integer had to be prime as a Gaussian integer. And so now, with what we just proved for the fundamental theorem of arithmetic for the Gaussian integers, for homework, you will be tasked with proving the following partial converse to that statement. Specifically, if we have a Gaussian integer a plus bi, with a not equal to 0, b not equal to 0, if z is a Gaussian prime, then the norm of that Gaussian integer is prime as an integer. And so you can use the fundamental theorem of arithmetic to prove this result. So to finish it off for today, we're going to set some results that will allow us to prove Fermat sum of squares theorem again in our next lesson. And the fascinating thing is that the properties that we have seen up to now pertain to the Gaussian integers. These were established by 1832 by Gauss. Yet its connection to the sum of squares theorem would not come until 60 years later when Richard Dedekind in 1894 used the Gaussian integers and their classification of primes, which is what we will be doing, to demonstrate that Fermat sum of squares theorem is also true. And this will give us a much simpler argument than what we did using Euler's descent lemma and reciprocity lemma previously. That being said, we are going to see that the reciprocity lemma is snuck into the argument, and the descent lemma is done away with by means of the norm. And so let's go ahead and do our first result in this direction. So let's go ahead and say we have a natural number n. So now we're back in the integers. If n is congruent to 3 mod 4, then there do not exist a and b such that n is equal to a squared plus b squared. And so here's the idea for this. So we're working over z mod 4. So we're working over the integers modulo 4. So proof. So in C4, so we have that a bar squared is equal to, so if we go through the list, so we have 0 squared, let me just do it this way, 1 squared, 2 squared bar, 3 bar squared. That exhausts our squares modulo 4, and that's the same as 0, 1, but 2 squared is 4, which is going to be 0, and so we have that 3 squared is going to be 9, which is modulo 4 is going to be 1, and so we have this here. So consequently, a bar squared plus b bar squared can either be one of the following properties. One of the following. We only have that, we know that a squared and b squared can either be 0 or 1. So this is going to be, if it's 0 and 0, we're going to have 0. If it's 0 and 1, we're going to have 1. And if a and b are both 1, we're going to have 2. And so that exhausts all the possibilities we have. So we're going to have one of these 3 possibilities. And so that's if this here happens. So as a consequence of us not being able to get back 3 bar, we now can conclude that there are no integers a and b such that n is equal to a squared plus b squared. And so consequently, there do not exist a and b integers with a squared plus b squared being congruent to 3 mod 4. And so that's what we have here. And so now that finishes off the proof for this. Let's look at the next statement. If p is a prime integer, then if p is congruent to 3 mod 4, then p is prime as a Gaussian integer. And so this will be just using this proposition we just proved. And you'll be tasked with this as part of your homework in 13.5.8. And now let us consider the next statement. So if p is a prime integer, if p is congruent to 1 mod 4, then p is not prime as a Gaussian integer. And so how do we go about this? And so one way we can do this is by adhering to Fermat's sum of squares theorem. But we are going to avoid that because we want to prove Fermat's sum of squares theorem in the next lesson. And if we assume it, then our argument will rely on this statement, making it circular. And so let's go ahead and give a direct proof of this without relying on that. And so what we do know is p is congruent to 1 mod 4. So that tells us that we know that negative 1 on p is going to be equal to 1. So by the quadratic character of negative 1, we have the negative 1 on p is equal to 1, since p is congruent to 1 mod 4. So therefore, there exists an x in the integers such that x bar squared is equal to, x bar squared is equal to negative 1 bar in the integers modulo p, and therefore, in particular, we have that x bar squared plus 1 bar is equal to 0 bar in the integers modulo p by the equivalent conditions of congruence. Equivalent conditions of congruence. There exists some integer k such that x squared plus 1 is equal to k times p. So we have this statement right here. And now we want to go ahead and make the following observation. We have x squared plus 1 equals k times p, but we are working over the Gaussian integers. And we can factor x squared plus 1 as x plus I times x minus I. And so we have this statement right here. And so what we want to show is that p is not a Gaussian prime. So now let's go ahead and do this by contradiction. So towards a contradiction, suppose that p is a Gaussian prime by Euclid's lemma, or by, I should say, the Gaussian, we have that p divides x plus I, or p divides x minus I. And now we're going to consider this in cases. So case 1, Suppose P divides x plus I. Then, so there exists some Gaussian integer m plus ni such that P times m plus ni is equal to x plus I. But this will be the same as Pm plus Pni equals x plus I. And so we have this here. But now this will only hold if the following is the case. Because remember, x is an integer. That's how we constructed it. X is an integer. And P, by assumption, is a prime integer. And so what this is saying is that then, in order for this to be true, we have that Pm is equal to 1. Sorry, Pm is equal to x. And Pn must be equal to 1. But Pn equals to 1 because P and n are both integers implies that P in absolute value must be equal to 1 since P is an integer, and that is a contradiction. And so that finishes case 1. And similarly, if we do case 2, now we suppose that P divides x minus I, the same argument, will tell us that there exists some m minus ni in the Gaussian integers, such that P times m minus ni, n plus ni, is equal to x minus I, which tells us Pm plus Pni equals x minus I, which in turn tells us that Pm is equal to x, and Pn is equal to negative 1. And so thus, the absolute value of P is again 1, contradiction. But this exhausts all the possibilities, so we conclude that P is not a Gaussian prime. And so in here we have essentially built into the argument the reciprocity lemma of Euler and how he argued. But the reason we want to prove this without adhering to Fermat-sum of squares theorem is that if we did, then everything that we prove from here on out will assume Fermat-sum of squares theorem. And so if we were to prove Fermat-sum of squares theorem using theorem 1.23.3, we essentially are doing a circular argument because we assume Fermat-sum of squares theorem here to prove it later. And so that would not give us logically a new proof. And so as a result, we went ahead, proved this directly without having to adhere to Fermat-sum of squares theorem. And now in the next lesson, we will be able to establish Fermat-sum of squares. And so the next two statements to finish it off for today, these are homework questions, and we will use these in our next lesson to prove the Fermat-sum of squares theorem. And so the first result is that if P is a prime integer, then P is prime in the Gaussian integers if and only if P is congruent to 3 mod 4. And as a follow-up, we have theorem 1.23.5, which tells us that if Z is a Gaussian integer, then Z is a prime Gaussian integer if and only if one of the following conditions hold. The norm of the Gaussian integer is exactly 2. The norm of the Gaussian integer is a prime integer congruent to 1 mod 4. Or the Gaussian integer is a prime integer, is a unit times a prime integer that is congruent to 3 mod 4. And so this is what we call the classification of Gaussian primes. And what we will see in our next lesson is that the proof of Fermat-Samos-Square's theorem is a consequence of this classification of Gaussian primes.